Yeah, so Nutzipper, let me come up with a simple example to start to illustrate what you're getting at here. So if I do something like new chan, then we can like chan send whatever, it doesn't matter what we send, and then maybe we have like two fours over here for whatever's from chan, and maybe we'll make these more interesting in a second, but for now they don't need to be. So like in this case, we have this one send on Chan and then two receives. And so we've got this race condition, right? And so if one validator tried to reduce this com with where the first receive is what coms with the send, but then a different validator tried to reduce the send with this receive, that's a different com. And so then we wouldn't be able to like do those things in parallel because they conflict with one another. And so if we modify this just a little bit so that we have two of these, now we could like marry up this first one with the first one and the second one with the second one, or we could sort of, like vice versa, flip them around. And in this case, they would be able to reduce in parallel because they're not going to conflict with each other as long as they don't, like both receives don't try to consume the same send or something. So then to get back to your question of like, how does this work with token transfers when everybody has to use the registry for a lookup at the beginning of every token transfer? What it comes down to is the registry implementation smart enough to know that the registry is, in that case, being used for read-only? And if it is, then those will commute just fine. So to sort of continue this analogy, we could do something like this. So this syntax with the two exclamation points, this is a persistent send. And it just means it's going to send this message over this channel as many times as necessary, like an unlimited number of times.
Yeah, remember that syntax.
Oh, nice. Okay, cool. Yeah, so in this case, since we're sending it infinitely many times, my understanding is that this send on channel will be treated as able to commute with other sends on the same channel because there's infinitely many of them. So when we pull one out, like when we consume one, it doesn't matter because there's another identical one there. And so like both of these receives could be reduced concurrently and it would work. And so if the registry works like this, then there's no bottlenecking there. But if it doesn't, then yeah, your intuition is totally right. Those are going to all have to be sequentialized, and the throughput would be reduced to whatever it is, which yeah, like kind of looks like it's about 100 comms a second today.
Okay, thanks.
Yeah. Oh yeah.
I cannot say I totally understood because it's quite complicated to get into how does this operate.
Yeah.
Well,
it's interesting. Actually, I wrote some testing code for this the other day. Maybe we can dig into that. So I have all these rholag files here, and they were all just generated by a computer, so they don't look that pretty. Maybe I'll make the beginning look pretty just for a second, so we can sort of see what's going on here, and then we'll get those further down. So it's just a bunch of the same kinds of comms over and over. So I'm using this channel at 1 to send and to receive. And then I just have all these M's for messages and C's for continuations. And like the continuations are trivial. They're just a string. And so this is the same as nil. It's like once we send this message and have the comma event, just do nothing. And the reason that I put these strings here is to see, because I think it takes a different amount of time depending on like how long your message is or how long your continuation is to actually pull that data out of the tuple space or to put that data into the tuple space. And so I wrote up all these scripts just specifically for the kind of testing you were talking about. And so maybe we can look into that a little bit. So there's this one, which is where there's a bunch of sends and a bunch of receives all on exactly the same channel. So I called those both linear because it's a linear send, like a single send, and a linear receive. And then there's this one, which is really similar. So you just notice there's like a million sends up here. They all look basically the same. And at the bottom, a single contract. So like every one of these sends will be able to com with this single contract. And then this is basically the same, but I used a persistent listen instead of a contract. This one's the opposite, right? This one has all of these linear receives, and then at the bottom just has a single persistent send. And then finally, this one's unique because we don't recycle the same channel over and over again. So that first line is on at 0, and the second line is on at 1. So now, unlike the registry problem, these are all unique channels, and it seems like they probably should be faster. But let's actually just run them and see, because I wrote this for the performance testing, but they haven't used it yet, so I don't know how they work. I still have my node running from node testing, but I think I want to clear it to get a fresh node. Oh, and I've noticed, have you guys noticed that the node crashes sometimes when you try to bring it down nicely? Like it's a fatal error in Java?
I got something that looks like crash only if I press Ctrl+C several times, but it always shut down nicely with a single one.
Okay, okay, nice.
I noticed that it doesn't shut down at all when I run out of memory.
Oh, really? It just kind of keeps hanging?
Well, yeah, you have to do a kill 9.
Oh, I see. Yeah. Okay, so let me start that thing up again. Oh, actually, so I don't have like, I think the core dev team has some pretty nice package for performance testing and everything, but my method is a little more crude. I basically just run these things and see, like, you know, count 1, 2, 3, like roughly how long it took when I'm doing this kind of quick and dirty way. So let's see, our node eval. And then maybe the first one we can do is this, like, both linear. And so that's just a bunch of regular old sends over the same channel every time. So we're going to have, in this case, I think it's 100. In fact, let's see. When I generated these, I told it to do 100 comm events. The message size is 10 characters long, and the continuation size is 10 characters long. So we'll see how long it takes to do those 100 comm events. All right. So I counted 4 cursor flashes before this message showed up and about 2 afterwards. And so that was when they were both the linear channels.
Joshy, do you have time command on your machine? You can measure with the time command.
Yeah, if you teach me how to use it, I think I do. I do have that. Is that what you're thinking of?
You just prepend the time before the command. The old line.
This one?
Yeah.
Oh, awesome. That's great to know. Okay. So which one is probably real is the one I care about most?
Yeah, real is the time which you count with your mouth. User time is the time that the CPU time used by the processor, or used by the command. So if you have several cores in your CPU, user time may be bigger than the real one.
Oh, okay. That answers I wondered how this could be a larger number, but maybe because some of it was happening at the same time on 2 different CPUs.
Yeah.
Okay, that makes perfect sense. So user is maybe the one that I really care about, I guess, then, right? Like how much CPU time did it take?
Depends on if you wanna understand how much parallelization inside your code.
Yeah, right. Okay. All right, cool. That's really good to know. So let's do another one then. Let's do the one where they're on unique channels. So this is almost identical code. We should still have 100 comm events. We should still have the same message size and continuation time, but this time they're not all on the on the same channel. Okay, interesting. So the real time was faster.
Yeah, actually, it means that the computing, the amount of work to be done is about the same, but it is elaborated in a more parallel-friendly way, I guess.
Yeah. So work to be done is about the same. You got that because this number is about the same, right?
Yeah.
Okay, but it took less actual seconds, presumably because it was more parallelizable. Like I got to use my multi-core more efficiently.
Yeah, as I understand it.
Yeah, well, I mean, that makes perfect sense, right? Because we still had 100 comm events of the same size, so it makes sense that there was the same amount of work to do. But when they're all on different channels, I guess it makes sense that they're more parallelizable. So maybe let's see how that changes if we do more. Whoops, that's not what I meant to do. If we do more comm events.
I think you have to look at the time used by the node also.
How would I look at that?
I guess you'd have to check it before you ran and then check it again after you ran.
You're saying like look at different timestamps in my node log?
No.
Oh.
You want to look at the CPU time. Let's see. If you do these options get me all messed up, but if you do a PS AUX into grep Java. Oopsie daisy, that's awfully long. What are the options to make that short?
So Jim, before we dive in too much on constructing a command, what's the big picture thing we're trying to accomplish?
We're trying to see how much CPU time was used by the by the node itself.
Oh, interesting. Okay, because you're saying like I run one command over here, rnode eval, but it might be a different process that's actually doing most of the work. Or no?
Yeah, I mean you're also using time on the node.
Yeah, right.
And I think that it may be that there's a direct correlation or whatever, or it could be different. That's my. I don't know if it would be different.
Yeah. Well, one thing at least that we can consider is the real time, because that I think that's a pretty good metric, right? It's going to stop calculating as soon as this eval returns.
I guess Jim is talking about that some time is spent on just spinning off the node. For example, 2 seconds just to start the node, and after 2 seconds, calculation starts. So if you increase the number of comm events, for example, from 100 to 1,000, you can see slight increase in real time because the most time is spent on spinning off the node.
Yeah, right. Okay. Well, so I know I have an idea then. So we should be able to see that as some kind of like intercept on a graph, I guess, right? Where there's a constant offset, but it just takes this long to spin up the Scala client and start the JVM and stuff.
Yeah.
So we tried it first with 100. We're about to try it with 1,000. Real time. Oh. Ah, boy. Come on. Okay, so what was all our data then? The first time we did it, we did both linear, and we got 7.009. right, next time we did it with unique channels, and that took 6.112. And now we're about to do this one. Both linear. Well, that doesn't make any sense. Oh, I have an idea. No, I don't know. I was going to say maybe we left stuff left over in the tuple space because I didn't restart my node each time. But I think with those files, there would be nothing left in the tuple space. Everything would get consumed because these are going to get consumed pairwise.
What? Yeah. Why don't you run the first one again? Let's see what you get.
I ran it with, run the first one again? Okay. So I got to go back to 100 comms. So that means I need to regenerate those rholag files. Okay. And now this is the first one, both linear with 100 comms. So yeah, this is the one that we're about to redo. So that's pretty interesting. Maybe I'll do it again with 1,000 just for a sanity check. Regenerate the rholag files. Rerun with 1,000 comms. Wow, that's so confusing. I guess, so maybe one interpretation is that it takes about 6 or 7 seconds just to start up the JVM and then the comms are insignificant.
Could be.
Yeah. Well, one way to try it is just to put a lot more comms. So we'll remake the contracts and rerun both linear. The other thing is this might just take longer than we're willing to wait with that many comms. I don't really know. Oh no, what? It didn't even seem to make a difference. Well, that's pretty confusing to me. You guys have any thoughts?
Not really.
If we want to get, it seems like it always takes 40,000. So if we do, or it always takes 7 seconds. So if we want 40,000 comms per second, we just need that many comms. And this is even the one where they're not on unique channels. This is where they're all on the same public channel. That's crazy.
Can you check the file? Is it really?
Yeah, that's a good idea. That's a good idea. Wait, that doesn't look right. Ooh, I think I know the problem. I think I was creating those files in the wrong directory. I was creating these other, okay. Let me show you what I did wrong. That was a great idea, Nutzipper, thank you. So I accidentally just created all of these, both linear, persistent listen, etc. But then I was running these ones. Good catch. Rookie mistake. So really, I think all of these numbers are here for 100 comms. Okay. All right, let's try to do that better now. Oh no, my system's slowing down. Uh-oh, sorry guys, stuff is freezing up. That's okay, we'll just do it from here. All right, 1,000 comms. I should have made sure those got bigger, but we'll know in the future, I guess. So we're working on both linear. That's now 48 kilobytes. Okay. Does this look okay? Now I'm going to run the right one that I just made.
It seems so.
Yeah, this is taking longer, definitely. Okie dokie. Oh, weird. So the user time doesn't seem to have changed that much.
Yes, yes.
Is that what you were expecting?
Yeah, I got the same results.
You did?
Yes, I got increasing of real time, but user time was pretty small.
That's interesting.
That's why I was thinking, why would that be? I was thinking about I/O, disk I/O blocks, but there is no writing or reading to the disk. Then I thought that maybe it is Java garbage collector working, but I haven't got an idea how to measure it.
Yeah. Wow, okay. Or I wonder if it's like, maybe it takes a really long time to just parse a file that long.
Actually, no, because I used a pretty small file, dupe contract, which
Right. That's one
we
where it's easy to
can,
parse regardless
yeah,
of how many comms. Yeah,
yeah.
good point. Good point. So wow, okay. So maybe let's bump down here to the unique channels one and see if we get a difference there. We had it seemed like maybe a small difference before. Yeah, same user time again. So you were doing that with dupe.row, you said, right?
Yeah.
Oh, that text editor crashed. I forgot. Oh, darn it. I wanted to just look at some of these other contracts. The one thing.
If you wish,
yeah, go ahead.
If you wish, I can find the link to the ticket with the graphs that I got.
Oh, that would be wonderful. Yeah, I didn't realize you had posted graphs. So I had tried to modify dupe.row a little bit because all the comms are over the same public channel here. So I tried a different one that would put comms over, well, most of them are over different channels. And I was curious to see if that would make it. But then I just was going to leave it to those core guys to actually do the testing.
can see in the chat the ticket.
Oh yeah, 2 pow 14. Okay, that makes sense. Oh, nice.
There's a increase in real time because there is some bug, not bug, but some special in our space, which will be fixed.
Okay. So what are the axes here? Just times that you ran it? You ran the same code multiple times?
Yes, I'm as you can see, I ran my code 11 times and made a slight breaks between 4th and 5th and 7th and 8th tries to just check maybe if it depends on the node uptime, but it's not. It's just evaluation time grows linearly from the number of evaluation. It's not really what we're talking about now, but as you can see, real time is much bigger than user time, which is
Oh
about
yeah,
to
these are the same
be
units on the axes here?
yeah
Second in both cases?
user time, yeah, real time and user time. So as you can see, user time is pretty stable, about 7 seconds,
Mm-hmm.
but the overall evaluation is much slower.
Yeah, okay. I'm starting to think maybe this is like what Jim was saying though. Maybe when we time like like I was doing commands like this, or you did something similar like this, right? Time rnode eval 2 pow 14.
Yeah, the same.
So it's possible that what we're doing here is basically like spinning up a thin client that just says, "Hey node, run this." Maybe its user time is really slow or fast, 8 seconds or 7 seconds or whatever. But all the actual work, like Jim was saying, is happening over here on the node, and we don't have a good way to time that.
So time command measuring wrong time. It measures just starting the node maybe, or some routines that are tied with the our node work.
Yeah.
But the overall work happen in GVM, inside GVM, inside another process.
Yeah.
It could be, yeah.
The tricky part there is I don't know the right way to time that other process because it has to be already running beforehand, and it takes a long time to spin up. Oh, you know what? There's the rholag CLI. I don't know exactly how to build it though. Let's see. I'm gonna keep that. Somehow you can build this if you do all the SBT stuff to like build the node. You get this thing called rholag CLI, which just does the rholag, not all of the like other node stuff. But I'm not that really much of a Scala guy. I don't really know how to build that thing. Yeah, this is definitely what I wanted. Oh yeah, right. And then once you have this rholag CLI, then we can. How did they do this? Oh, this is just some file name. That's just some rholag file. Jim or Nutzipper, have you guys ever built this thing?
Nope.
Yeah, me either. I don't think it's that easy. I know Dan does it. Maybe we could try to get him to do it. Yeah. Okay, well that's all really interesting performance-wise. That's good stuff to think about. What should we talk about that more, or do you guys want to do some other rholag stuff, or what are you thinking?
I guess we can. Jim, go.
Yeah. You can get a rough idea if you run the command I just pasted in there before and after you run the eval.
Oh, wow. Okay. Pipe grep Java, pipe sed.
Yeah. So paste that in, then the rnode command, the rnode eval, and then paste that in again.
Okay. And I'm trying to do this like quick so I don't
No, you
waste
just
it.
put the semicolon rnode.
Oh, got it. Okay. I guess we'll just do that one.
And then I paste it in again.
Like this?
Yeah. And this gives you time used by the back end, which it uses time whether or not you do an eval.
Mm-hmm. So
So
what is it telling me now?
they're telling you that it used 3 minutes and 7 seconds of CPU at the end, and then you go at the beginning, it used 2 minutes and 55.
Oh, this is how much CPU it's used just like cumulatively since I've started it?
Right.
Okay. I understand.
So that seems the right work that we should measure.
Hmm.
That
So
is
that's
Java doing.
yeah, that took 12 seconds basically. Okay, so let me just start to wrap my head around this a little bit. So Jim, if I just run these twice back to back like this, I should get pretty close to the same number both times, right?
Correct. But remember, the node is doing, well, actually, the node's not doing other work.
It's especially not doing much when it doesn't have any peers or anything.
Right.
Yeah.
My node is using time all the time.
Yeah, because yours is always on network, right? And
Right.
listening to Discord and stuff. Yeah. Okay, so that's good to know. So what did we just run then? I don't remember how many lines of code we had in there. That was for 1,000. Okay. So let's try it with 100. So that took about 12 seconds last time. Regenerate the
Because you're
content.
only getting output in seconds, you may need to use more, increase the amount, like to 2,000. You see?
Yeah, you're saying because I can't see that it was point however many seconds, milliseconds.
Yeah, right.
Yeah. What did I just make it? Oh, I made it. Okay, well, let's do the short one at 100 and see what happens, and then I'll do a big one. Okay. There's still 308 like before. And now 309. Okay, so we don't have that much precision, but like roughly 1 second. Okay, and then for 2,000 comm events, it took roughly 2 seconds.
Did you rewrite the script, row script?
I think I did. I have 2,000 and I have it saved, and then let's just look at the file.
But you didn't run make rholag JS, or did you?
I think I did. Oh. No, I think you're right. I didn't. Yeah, wait. Yeah, you're right. My bad. My bad. Okay. Yeah, this one's taking longer.
Yeah. What did it take with 1,000?
I don't know. I don't remember if I ever did that. Okay, so
First
41 minus 11. So that took about 30 seconds of CPU time.
I thought we tried 1,000. Maybe you should try 1,000.
Okay, make rholang JS, and then the time command. Oh. Hey guys, I might have to jump out a little bit early today. I just realized I missed a call.
Yeah, sure.
Okay, so that went from 41 to 53. So that was 12 seconds for 1,000 and about 30 seconds for 2,000. So I'll show you guys this just so you know where it is before I jump off. I did make a PR. Oh, Zoom is messing. There we go. So the code that I just showed you with making all those tests and everything is in this pull request, in case it's interesting to play with. So here's the link for you. I do have to jump off though. It's actually a sort of a job related call, so I think I better be kind of quick about it.
All right.
Yeah.
Thanks, Joshy. Bye. Bye.
Yeah. Nice chatting, guys. See you next time.
See you, Jim.